Hi, my name is Edwina, and this is my colleague Ye. We're both from LinkedIn, and today we're going to discuss metrics-driven tuning of Apache Spark at scale. LinkedIn has a diverse Hadoop ecosystem supporting many different kinds of computation engines, including MapReduce, Pig, Hive, TensorFlow, and Spark. Over the past few years, these workloads have driven our clusters to reach a very large scale with over 10 clusters, tens of thousands of nodes, thousands of users, and several thousand applications running every day. Spark has been becoming more and more popular at LinkedIn. Over the past year, we've seen a rapid growth in the Spark workloads running on our clusters. This slide shows a growth trend for one of our clusters. We measure Spark usage using two metrics, the number of applications per day and also the average daily resource usage. For this cluster, we can see that the number of daily Spark applications has increased by a factor of 2.4 times over the last 3 quarters. And the amount of compute resources being used by Spark has also been increasing. Right now, Spark accounts for about 25% of our compute resources. And this works out to about 1.6 petabyte hours per day. We're also seeing a diverse set of use cases for what Spark is being used for, spanning across relevance, ETL, machine learning, other kinds of analytics, and also metrics. We took a closer look at how Spark is being used on our clusters, and we discovered that only about 34% of the allocated memory was actually being used. Look at the sample application with 200 executors and allocating 16 gigabytes for each executor and the driver. However, it's only using at most 6.6 gigabytes for any executor, and it runs for an hour. This means that there's 1.8 terabyte hours of wasted memory. Now multiply this by thousands of applications running per day, and this adds up to a lot of wasted resources. With how quickly Spark usage has been growing on our clusters, we need to make sure that our infrastructure and compute resources are able to keep up. One option is to add more hardware. However, this costs money, and also it's very complex to support. Earlier today, Konstantin and Eric from LinkedIn had a talk about scaling Hadoop at LinkedIn, and they described several different challenges that our group has faced as far as being able to scale out to handle more data, more users, more nodes, and higher workload. Another option for how to handle this problem is to try to make sure that we make good use of existing resources. Since only 34% of allocated memory is actually being used, if we can make our Spark applications more efficient, then we can run 2 to 3 times as many applications on the same amount of hardware. This was motivation to try to see what we could do to improve efficiency on our clusters. So we have a diverse set of Spark applications. Some of these applications are ad hoc or exploratory. They're using Spark Shell or notebooks to basically do some exploration. And we don't necessarily always know for these kinds of applications how much resources they're going to use because the users don't always know what they're planning on doing. However, a lot of our Spark applications are regularly scheduled runs that run every day or every hour. And they're basically the same application running on different sets of data. So we can get a pretty good sense from the historical runs how much resources they're going to need and if there's any resources being wasted. Tuning Spark applications can be pretty complicated. There's a lot of different metrics to look at to determine if an application is well tuned. And there's also a lot of different configuration parameters. Our Spark users are data scientists and software engineers. They're focused on improving or developing new algorithms, finding new insights, or creating new applications and features. They're not necessarily Spark tuning experts, and they don't necessarily want to spend a lot of time tuning their Spark applications. They're not always familiar with what the different Spark configuration parameters are, which ones they should set, or what values to set them to. So they've often come to us as the Spark team for help with tuning their applications. However, this really doesn't scale. We're a small team, and there's a lot of Spark users, and the number of Spark users is growing. Our users don't want to have to wait days or even weeks to get some help from us. It's very frustrating for them, and it's not a good use of their time. So we want to make sure we make efficient use of our compute resources, but we also want to make sure that our users are productive and they can iterate quickly on their projects. Data sizes and engineers cost even more money than hardware after all. So it seems like we have two competing goals. Is there some way we can have both an efficient cluster and productive users? At LinkedIn, our solution for this problem is Dr. Elephant. Dr. Elephant is an open source project started at LinkedIn that monitors performance and provides tuning advice. It was originally created for Hadoop MapReduce jobs, and we've added support for Spark to Dr. Elephant. It uses heuristics to determine if applications are well-tuned and identify any problems. It then provides customized, actionable advice to our users for how to tune their applications. Dr. Elephant is also able to compare performance changes over time as users tune their applications, or if the application itself changes. This slide shows an overview of how Dr. Elephant works. Dr. Elephant gets information about what applications have run on a cluster from the resource manager. Then for each application, Dr. Elephant queries the history server for information about the application and metrics for it. Dr. Elephant then uses a set of heuristics to analyze the metrics and information to determine if there's any problems. If it flags any issues, it does some further analysis to determine how the issue can be fixed. The results are stored in a MySQL database, and users can access the Dr. Elephant reports via the web UI. While working on adding support for Spark to Dr. Elephant, we ran into a couple of challenges. One was determining what heuristics should be for determining if an application is well-tuned, and what metrics to use for each heuristic. I'll talk about that next. Another problem we ran into was getting the metrics at all. Dr. Elephant gets the metrics from the Spark history server, and the Spark history server wasn't able to scale to keep up with the growing number of Spark users and Spark applications that were running. For the second part of the talk, we will discuss how we were able to scale the Spark history server. Now let's take a look at Spark memory, heuristics, and metrics. This slide shows an overview of the different Spark memory regions. Each executor runs inside a container. Executor memory is specified with the configuration parameter Spark executor memory. Executor memory is divided into the user memory region, which stores user data structures, and the unified memory region. The unified memory region is further subdivided into execution memory and storage memory. Execution memory is used for computing shuffles, joins, sorts, and aggregations. Storage memory is used for caching RDDs and broadcast variables. This is a unified memory region because execution and storage can borrow from each other if one area needs more memory and the other has some to spare. Both can spill to disk if needed. The fourth memory region is the overhead memory region. This is memory that's allocated for the container, but not part of the Spark JVM. Spark also uses this off-peak memory. It's used for NetI and NIO buffers, thread stacks, and OS overhead. Now let's take a look at some of the heuristics that Dr. Elephant uses to determine if a Spark application is well-tuned. One thing that Dr. Elephant checks for is to see if Spark executor memory is set to a reasonable size. I'll check the value of Spark executor memory and compare this against the max peak executor JVM used memory. This is the maximum amount of JVM used memory used by any executor over the lifetime of the Spark application. If there's a big difference in these two values, allocated and used, then we know that there's memory being wasted, and we can ask the user to lower the value of Spark executor memory. We can also provide a new recommended value based on the max peak JVM used memory. It's possible the value could be set even lower and garbage collection could be done more frequently, but this is a pretty safe value. We do a similar check for the driver. We'll compare Spark driver memory against the peak JVM used memory for the driver. We also look more closely at the unified memory region. We'll calculate the amount of memory that's been allocated for the unified region and compare this against the max peak unified memory that's been used. Again, if there's a big difference in the value, then we know that there's memory being wasted. And we can recommend that users lower Spark memory fraction to make the unified memory region smaller. Of course, it's possible that executor memory overall has been over-provisioned, and there's wasted space in both the unified memory region and also the unified memory region. In this case, we would go with the first heuristic, which asks users to lower Spark executor memory. Another thing Dr. Elephant checks is to see if there's any execution memory being spilled. Spark works best if it's able to keep data in memory. If it has to spill execution memory to disk and then read it back in, the extra overhead will slow down the application. So Dr. Elephant will identify which stages have execution memory spill, and also check to see if there's any skew. So if there's a few tasks that are processing large amounts of data and need to spill, and other tasks that process less data and don't spill, then we can ask the user to take a look at their application and see if they can make the partitions more even. If there aren't any really large tasks processing a lot of data, then the chance for spill is reduced. We'll also check to see how many tasks are running for the stage. If there's a small number of tasks and each task is processing a lot of data, then we can ask the user to increase the number of partitions by setting Spark SQL shuffle partitions. If there's more partitions and less data being processed by each task, then there's less need for spill. Of course, having more partitions increases overhead on the shuffle service, so there's a trade-off here, so we don't want the user to set the value too high either. We'll also have to check to see how many cores are being allocated for each executor. The number of cores determines how many tasks can run in parallel on the executor, and executor memory is split across all the concurrently running tasks. So if there's more tasks running concurrently, then there's less memory available for each of them. Whoops. So if the number is set pretty high, then we can ask the user to lower the number of cores for the executor and perhaps increase the number of executors so that they can maintain the level of parallelism. And if Spark executor memory is set to a pretty low value, they can just increase that as well. We'll also check to see if Spark is spending too much time in garbage collection. The Spark Web UI already does this check and flags in red any executors that is spending too much time in GC, and Dr. Elephant checks for this as well. If we see this problem, then we can recommend increasing executor memory. We've taken a look at a few of the heuristics that Dr. Elephant uses to determine if a Spark application is well-tuned. This slide shows an overview of the process. Our users write Spark applications and run them on a development cluster. Dr. Elephant analyzes each of these applications and determines if they're well-tuned or not. If it sees any issues, it will notify the users and tell them how to fix the problems. The users can then quickly make the changes and rerun their applications. Dr. Elephant also serves as a gateway between our development cluster and our production cluster. Only applications that are well-tuned and pass Dr. Elephant's check can be promoted to production. This helps us keep our production cluster healthy by only running well-tuned, well-behaved applications. Dr. Elephant also monitors the applications running on our production cluster. As the amount of data changes, or if the distribution of data changes over time, then the behavior of the application can change as well. So Dr. Elephant will notice if an application that used to be well-tuned no longer is well-tuned anymore and can notify the user. Now let's take a closer look at how metrics are processed in Spark. The driver assigns tasks to the executors. The executors perform the tasks and send the results back to the driver. The executors also send heartbeats to the driver at regular intervals, by default every 10 seconds. The heartbeat notifies the driver about the health of the executor and what progress is made. It includes task level and executor level metrics. The driver collects these metrics and aggregates them, and they can be seen at the executor level and the stage level on the web UI and also via the REST API. Dr. Elephant uses the REST API. The driver also selectively logs some of these metrics to the Spark history logs so that the information is still available after the application finishes via the Spark history server. While working on memory tuning, we noticed that there wasn't actually a lot of visibility in how Spark uses memory or how much memory is used for different memory regions. So we decided to add some new executor-level memory metrics, including JVM used memory, execution, and storage, and then we can calculate unified memory by summing execution and storage. We're currently working on the upstream ticket, and we hope to share our work with the community. Dr. Elephant and our users both use the history server to get information about applications and metrics. Our users use it to debug any failed applications and also any really slow applications. Dr. Elephant uses the Spark history server to gather metrics to analyze applications to determine if they're well-tuned or not. However, as the number of users and applications has grown, the Spark history server hasn't been able to keep up with the workload, and it's had a lot of problems. I'll now pass this talk over to my colleague Ye, who will discuss how we've made the Spark History Server a scalable, efficient, and reliable source of Spark application metrics.
Thanks, Edwina. So Spark History Server is a critical component that enables viewing history of Spark applications. Its main functionality involves consuming history files generated by Spark applications, and then serving the histories to either the users via the web UI or Doctor event via the REST API. Under the hood, Spark History Server consists of many internal components. The two most important pieces are two groups of databases. The first group, which is named listing databases, consists of a single database that stores the metadata for every Spark application. The other group, which is named applications database, consists of multiple databases, each storing detailed history information for one Spark application. The listing databases serves the web UI that renders the application list on homepage, while the application databases serve the UI that renders the application history details. So in the most recent version of Spark, these two databases are converted as a persistent storage leveraging local disk with LabelDB. They serve as the caching layer between the HDFS history files and the in-memory data. This version performs much better compared with the original or in-memory version. However, in reality, when History Server handles requests at scale, even with the improvements mentioned earlier, its performance is still unsatisfactory. Users cannot rely on History Server to access the history UI timely, while Doctor event faces troubles accessing the metrics through History Server REST API stably. When we operate Spark History Server, we noticed these four major issues that prevent it becoming a reliable history or metrics provider. Users often find the applications are missing from the History Server web UI homepage, and even they can find it on History Server, it takes a long time to load. If the History Server to be loaded happens to be large, it could also completely store the History Server. On the other hand, when Doctor event fetches metrics from History Server, where it generates high-volume concurrent REST calls, History Server cannot properly handle this request. Let's take a closer look at the first two issues. In a typical scenario, after a Spark application is submitted and running towards a failure, the users would want to check out the root cause for the failure. However, in most cases, the application cannot be found immediately right after finish in Spark History Server without some kind of delay. Such delay leads users to believe their applications are missing from History Server. Even worse than that, after waiting for a while, the missing applications show up on History Server, users could still experience a delay up to half an hour for History Server to know the application details before they can check out the root cause of the failure. After we investigate the internal of History Server, we realized that the listing delay is related to extracting the metadata from history files and putting them into listing databases. In order to extract all the necessary metadata, the history file needs to be processed multiple times. Each time a history file needs to be it's processed, it consumes one of the limited threads on History Server. And the time it takes to parse the whole history file is proportional to the size of the history file. When there are many history files to be processed, we can imagine how slow the process could be if there are multiple large history files occupying all the available threads on History Server. This leads us to realize that in order to decrease the listing delay, we have to make the metadata extraction process more efficiently. After looking at the available options, we decided to encode the history metadata information using HDFS extended attribute. This enables us to retrieve all the necessary information, metadata, without actually reading the history file. It further enables us to decouple the processing time of history file from its size. This change significantly improved the throughput of history server, extracting metadata from a large amount of history files. With this issue causing the listing delay addressed, we further investigate the cause of the second delay, which is extended loading time of history details. As mentioned earlier, application databases serves as a caching layer to store history details. If the application database already exists, the loading delay is acceptable. However, history server will not try to create the database for each application automatically, and it has to be triggered by an external request. While creating the DB, the full history file needs to be processed, and this cannot be avoided. If the log file is large, the database creation time will naturally be longer. While the Spark community has plans to reduce the loading time by incrementally processing the history file, we still need an alternative solution before it's available. We observe that in most of the case, our users won't access the history details as soon as the application finishes. And the gap could be tens of minutes. So since we cannot effectively reduce the history file processing time, the only option for us is to start the DB creation process as early as possible. And this is exactly what we did. So we have a kind of a robber that query history server to start the DB creation prior to the user's request. With this improvement, we successfully decreased the listing delay to within 1 minute. And for 90% of applications, their application database will start to get created within 5 minutes right after they finish. But with the first two delay issues addressed, history server now has a reasonable performance under a normal workload. However, if the size of the history file or the number of concurrent requests becomes too large, history server still faces scalability issues, which imposes hurdles for Dovetail event to fetch metrics at scale. Such scenarios are getting more and more common with our increasing number of Spark applications and Spark users. In early days operating history server, while we have multiple versions of Spark binary, including 1.6 and 2.1, and now we have 2.3, it will enter a contiguous garbage collection and store processing any request from time to time. In worst scenario, Spark history server will stay in GC status for hours until being restarted. After analyzing the heap dump, we found that there is one thread taking 23 GB memory. And it turns out that not all events stored in history files are necessary to be processed. And if a history server can ignore these events when processing history files, it could significantly reduce the memory footprint. In Spark version after 2.1, they have removed these events handled in the driver and also logged in the history files. But if you have some older version Spark binary, you will encounter these problems. Another issue we find out is how history server handles larger amount of concurrent requests invoking the REST API. When the number of concurrent requests goes beyond certain threshold, Spark history server will fail into a state where it cannot associate these requests with correct handlers. This would lead to issues where Dovetail event would get empty response from the REST calls. And after investigation, we realized this is a synchronization issue in history server itself. We're trying to contribute all of our internal patches with these history server related improvements to the community, and some of them has been merged into trunk. Some of them still under like rebasing on the trunk because we work on the Spark 2.1 internally. And after all this improvement, users can always find the application on Spark history server homepage within 1 minute. And for 90% of applications, their applications DBs will start to create as soon as possible. And now History Server can act as a stable and reliable service and can handle high volume concurrent requests for docket event. We are planning to continue our work on tuning. Right now, there isn't much information on off-heap memory, so we would like to gather more information for this to be able to check and make recommendations for memory overhead. We also plan to look into skew in how tasks are assigned to executors, and also skew in the amounts of data and time of tasks for a specific stage. We would like to do some analysis and be able to make recommendations to users to improve their performance of Spark applications. We'd also like to investigate the information provided in the DAG to see if we could, this could be used to provide useful information for users. And also with the increasing amount of Spark applications in our cluster, it's reaching the maximum capability of a single node history server. We would like to scale out history servers to multiple nodes, and they can coordinate together to handle more and more daily Spark applications in our cluster. Yeah, and that's pretty much our talk. Questions? Yeah.
But very nice talk. So I have a question about the tuning in the dev and the user results to optimizing the production. So have you run into any issue that it's well tuned in the dev, but actually you don't see the same results in the production, which means there might be some difference in the specification of the servers?
Usually it's pretty similar. Okay, it's not always similar because different kinds of workloads in production and development, so that would also multi-tenant cluster, so the number of other applications running and waiting for containers, executor containers, could also cause a difference in behavior. The amount of data that we see in the dev cluster and production cluster could also cause differences. And also we've noticed that sometimes the settings for the configuration variables are actually different between development and production. It's not actually automated as far as keeping them in sync, so yeah.
But even it's different. Like we have Docker event running for every Spark applications, running in both development cluster and production cluster. Users can still tune based on the new report generated from the production cluster.
Okay, I see.
Yeah.
Thanks.
So is this tuning on a per job level?
It is.
Yeah.
So this is basically when I submit a job, I'm going to set these parameters, and then it will run, and the next job will take its own set of parameters.
So you mean it's automatically pick the best configuration, or?
I mean, does any of these parameter changes require a Spark restart?
It
Yeah.
would be, yeah.
Yes.
Yeah.
Because we only get those metrics after the job finish, and then the report can be generated by Docker event.
So job A and job B, like how would they run with different sets of Spark settings?
The user would have to set them right now. I mean, ideally it would be kind of nice if Dr. Elephant, you could just hit a button and it would sort of set it for your application automatically, but we don't have that support right now. So.
No, I mean.
Okay, sure.
Yeah.
What I was saying is like, so for job A, you have a certain set of parameters, right?
Yes.
Now, if I run job B with a different set of parameters, will Spark just pick it up, or will you have to restart the cluster?
No, the job configuration is specifically to specific job. So different job can have different configurations. Overall, in our cluster, it has the default configurations that's specifically tuned by us. But for any other jobs, users can try to change the configuration by themselves, and it will be adapted to only that job. So even job A and job B, there is no relationship. Like the configuration can be totally different. Yes.
Usually there's a configuration file that users can specify what
Yes.
they want the Spark configuration parameters to be, and that would be on a per job basis.
Yeah.
Just curious, did you
It's a mix. For ETL, it's a lot of it's SQL, but for a lot of development folks that are trying to do some kind of analytics or machine learning, it's usually not.
So did you find the tuning, do they depend on what type of Spark jobs are they kind of generic on they don't care about?
We haven't actually checked, I guess.
I think the basic idea for these metrics should be generic to different types of Spark applications because we gather the runtime resource consumption. It doesn't matter whether it's a machine learning job or it's not. Yeah. What do you mean by the change? So you mean developer change some of the code or the logic inside?
Yeah, let's say a developer changed some code and then the place changed within it, but then it changed the performance configurations. So how does Docker then keep track of what changed and then according to that, how will it know like what will the best run?
Yeah.
We're tracking changes in the metrics that we're monitoring.
Yeah.
So if those don't change, even if they change the application, then it's pretty much okay. If suddenly it's using a lot more memory or a lot less memory or something like that, then at that point we'd kind of flag it and notify the user to try to do some tuning.
Does it keep track of like the metrics per query or per stage also?
It depends on the heuristic, I think.
Yeah, I think Docker Elephant right now doesn't track, but we have our own tracking, which also queries Spark History Server that stores each stage metrics onto HDFS. We have some kind of tracking mechanism to track every Spark application's metrics.
Yeah.
But I think,
Dr.
but that's a good suggestion that we can add it to Docker Elephant, like tracking the stage changes. So currently, Docker Elephant generates reports for every applications running in every cluster right now. And it will try to track the performance changes. And every day it will try to send out an email to those corresponding users saying, okay, your application's performance changed dramatically. You need to tune it. Yes. Yeah, it changes. I mean, the performance might get changed if users change their logic inside the code, right? Yeah.
Is there anything you can share about the roadmap for Dr. Elephant and new features that you're working on?
More memory tuning. So for off-peak memory, we'd like to get some more information about that because sometimes the container will get killed by yarn for using too much container memory. So we'd kind of like to be able to give users some idea about that and trying to take a look at the DAG to determine if we can kind of look at the logical and physical plans and try to give the user some useful advice from that as well.
Because all this also requires a Spark code change to get those metrics in. Yeah, and we are working on that. Yeah.
So I noticed that most of this is memory-based tuning. Is there going to be a more common executor suggestion addition to Dr. Elephant? Or do you engineer that?
We're using dynamic allocation in LinkedIn, so cores, yes, because that's set. I guess number of executors, they would get deallocated if they're not being used. But it could be useful depending on if users, other people are using dynamic allocation in their clusters or not. So cores are useful though.
Not interested in using Dr. Elephant in my organization. I understand it's open source. Like, do you guys have recommendations to like sitting on a server by itself, like slider app? Like, what would I do to get started?
It's sitting on a single node, and you just need to start making some configurations, like where is your history server, or for MapReduce jobs, you just need to tell where is the folders logs for the job history files for MapReduce jobs. Yeah, and that's pretty much enough. Yeah.
Yeah,
It's on
I guess
GitHub, on LinkedIn GitHub page. Yeah.
one warning is that some of the metrics that our LinkedIn Dr. Elephant uses isn't available in open source Spark right now, so there is some additional complexity.
You still need to wait the PR that Edwina showed to get merged, and currently she has submitted the PR, waiting for the review, got some comments,
comments.
fix the problems. Yeah.
Yeah.
Actively working on the PR right now. Yeah, we also want to get those merged as soon as possible.
And then we would need a Dr. Elephant side changes to work with the new metrics and stuff. So
Yeah, but
as
if you
far as
want to
open
try it
source-
out, yeah, if you want to try it out, you can just like take the PR and then apply the changes.
It's actually a little different from what the Dr. Elephant has due
Okay.
to the code review comments. We do need to get it in sync.
Yeah, thank you.
Welcome.
Is there a way to get some heuristics without running the job in dev?
Well, it needs to, Dr. Elephant needs to build a query Spark history server and look
Yeah.
at the information. So as long as I have the
You
Spark
mean-
history server,
Like, based on what you have seen having run and what you could find,
Oh,
what do you think
the
of
analysis.
Yeah.
something that you don't have, because you need a separate cluster and some jobs might be long.
So basically, kind of based on what we've seen so far, be able to make some recommendations on the application.
Mm-hmm.
It seems like an interesting area to explore.
Yeah.
So we had some other teams that are have been working kind of on trying to do some machine learning analysis and try to cluster applications that are similar or not, but it's really kind of exploratory right now.
Yeah. Okay.
Let's say you run a Spark shell, right?
Uh-huh.
So inside the Spark shell, you can run multiple, let's say, SQL queries or something. Right?
Yes.
So for you, then this Spark shell, is that treated as one job? Or
Yes.
Yes.
you cannot track the metrics for each individual queries inside the shell?
Yeah, I think this is kind of for Spark Shell jobs because user can type any queries they want, right? I feel like it doesn't make too much sense for tuning here. Yeah, most of our tunings are for our scheduled jobs through Azkaban. Yeah.
Yeah, the scheduled ones are, I think, about 90% or so. So
Yeah.
yeah.
Oh.
Tie a Spark job to
Oh.
a user.
Okay. What? Pardon me?
How do you tie a job
To
to
the user. The information is stored in the environment, the Spark environment.
Yeah. So we
the history
inject
log. Yeah.
we
Oh,
inject the
inject it.
user information into the Spark environment through Azkaban. So, and then through the logs and history server REST APIs, we can get those information about like which job, which Azkaban workflow, which project, everything there.
So Azkaban is the schedule that we use at LinkedIn.
Yeah.
So,
It's
yeah.
also open sourced.
Yeah.
Yeah.
It does. The Spark history supports mobile versions of Spark, but just the Spark history server needs to be the latest version. So we have run multiple versions of Spark on our clusters, and it's been able to handle that.
Yeah. You need the
right.
PR.
Yeah, that's the one thing.
The PR currently applies to the trunk. So
Yeah.
you might need to get some change by yourself to add those, to backport those to like older versions, 1.6, 1.3. Yeah,
We
but
have-
without this PR, it still can work, but they cannot get enough metrics here. Yeah.
Yeah, I think this was originally started on 2.1, and there were
Yeah.
some very significant changes between 2.1 and 2.3, so the backport isn't actually very easy. But we could probably provide a 2.1
Yeah.
version.
I don't really have a question for this. What tools you guys use at LinkedIn to schedule Spark jobs?
Azkaban.
Awesome.
Yeah, Azkaban. It's open source. You can check it out. Yeah. Okay.
Okay. I guess we're
Yeah. Okay.
done.
Yeah, we can take questions
that's
later.
helpful.
Yeah.
Yeah.
Thanks.
Okay, thanks.